For the stability of equilibria for autonomous ODEs, there are three types of stability. So the first type of stability is a stable equilibrium point, which is an equilibrium solution that attracts nearby trajectories. Alright, so over on this side, the solution y is equal to -2 is attracting nearby trajectories. So things that start a little bit below -2, so for instance at -3, will eventually, they'll asymptote to the -2 equilibrium solution. And also things that start a little bit above the -2 equilibrium solution will asymptote to y equals -2 as t goes to infinity. So y equals -2 is a stable equilibrium solution, and it's usually signified by a filled circle. And this here, we're going to be plotting the phase line. It's really just the stability of all the different equilibrium points. Alright, so -2, stable equilibrium solution. And an unstable equilibrium solution is one that repels nearby trajectories. So an unstable equilibrium solution is, in this case, it's y equals 3. Because even if you start really, really close to the y equals 3 solution, if you're just a little bit above y equals 3, you'll eventually go away from y equals 3. And if you start a little bit below y equals 3, you will go away from y equals 3. So it's repelling y equals 3, the equilibrium is repelling nearby solutions, so it's an unstable equilibrium solution, usually signified by an empty circle. And then the last one, which doesn't occur too often, is called a semi-stable equilibrium solution. And it's semi-stable because it's stable on one side and unstable on the other, meaning that it attracts nearby trajectories on one side and repels nearby trajectories on the other side. So the solution y equals 0 is a semi-stable equilibrium solution, because if you're a little bit below 0, you end up repelling the trajectories away from this equilibrium solution. But if you're a little bit above 0, then you're going to attract trajectories towards the y equals 0 solution. Semi-stable equilibrium, also called half-stable sometimes, is usually signified kind of as a combination of the unstable and stable. So this one has an unfilled circle on the bottom and then a filled circle on the top. So the unfilled circle is for the unstable side of the equilibrium solution, and the filled half circle is for the stable side of the equilibrium solution. Alright, so you can tell the equilibrium solution by plotting a direction field, which we have the lines for here. So this particular equation is y prime equals 1/10 y squared times y plus 2 times y minus 3. And that's also where we got our equilibrium solutions, right? That's the positive 3 equilibrium, that's the -2, and that's the 0. For the y minus 3, y plus 2, and y squared. So you can use the direction fields. That's a little bit of work though. There's another way to do this. So another way you can do this is, okay, well, what if we say y prime equals some function f of y, and in this case it's 1/10 y squared times y plus 2 times y minus 3, and we're gonna kind of plot f of y, and I want to take off my arrows because there's going to be more arrows in the plot here, but f of y, and then here we've got y, and we're going to have some equilibrium solutions. We're going to have an equilibrium solution at -2, so we know that one is going to be stable here, so I'm just going to fill that in. So that's y equals -2. We're also going to have another equilibrium solution at y equals 0. So I'll put that one right there, and that one was semi-stable. Got to make sure I rotate this correctly. Alright, so like that, and then this side filled in. Alright, so that's going to be y equals 0. And then we're going to have another equilibrium solution at y equals 3, and that one is unstable. So I'll say y is equal to 3. So we know that from here, and we have f of y, we're actually going to plot it's kind of like plotting y prime against y, because y prime is equal to a function of y. So if you actually plot this out, like 1/10 y squared, y plus 2, y minus 3, on this line, it ends up looking something like this. Something like that. So another thing you can do here is you can actually tell which way the direction field lines are going to go. So if y, this is, f of y, that's y prime. If y prime is equal to 0, we're at an equilibrium solution, it doesn't move, it stays there. If we're equal to y equals -2, equilibrium solution doesn't move, y prime is 0. Y equals 0, equilibrium solution, y prime is 0. The value of y doesn't change. At y equals 3, equilibrium solution, y prime equals 0, so y is going to stay at 3 forever. Well, so then you have the stability here. So if y prime is negative, which it is right here, then that means the value of y is going to decrease. Y prime is negative. If y prime is negative, then you're going to end up going, y is going to decrease, it's going to move left on this line. And it's also going to be a much larger arrow in the middle because the derivative here is most negative right there. All right, over here we have y equals -2. If we're a little bit to the left, so let's say y is equal to -2.5, then y prime comes out as positive. If y prime is positive, that means the value of y is increasing. If the value of y is increasing, it's going to be moving right, because towards the right is increasing values of y. So you'll have, a little arrow here, but it's getting more and more positive, so the arrow is going to get bigger and bigger and bigger as you go to the right. It's actually going to move faster and faster. That's corresponding to these slope field lines getting steeper and steeper. It'll actually move faster when you're further away. All right, so now same thing over here. So this part was y prime is greater than 0. Y prime was less than 0. Here again we have y prime is less than 0. So that means that if y prime is less than 0, the value of y is decreasing. If the value of y is decreasing, then if we start somewhere on this line, the value of y will move to the left. And again, so we'll have kind of small arrows near the stability points, because the value of y prime, it's negative, but it's not that big. Then we'll have the biggest value in the middle there, because y prime is most negative. Then again, so now we're going to y is a little bit bigger than 3, so let's say y equals 3.5. In this section, y prime is greater than 0. Okay, y prime greater than 0, that means y is increasing. If y is increasing, that means the value of y is going to increase. So we're going to move to the right. And so here we'll have a little arrow because we're kind of close, but it's going to get really, really, really big as we go further and further out. And so from there, from these arrows, you can also see the stability. So, if this is a stable point, all the arrows are going towards it from both the left and the right. If you're nearby this point to start with, you're going to have an arrow that's pointing you towards the stable equilibrium solution at y equals -2, and you'll end up approaching there asymptotically. This semi-stable point is a little different. So on the left-hand side, we've got arrows going away from it, so that's the unstable side. But on the right side of this semi-stable equilibrium point, we have arrows going towards it. And the reason for that is, this one passed through the axis, this one passed through the axis, this one just touched the axis but didn't cross it, and that was from the double root. So that's why this point is semi-stable, and you can tell which side it's stable on, which side it's unstable on. Then over here, this is unstable, and we look at the arrows. All the arrows, if you're a little bit away from the equilibrium point, are going to be heading away. So all the arrows leave, so that means this is an unstable equilibrium point. One more way you can determine the stability of equilibrium points is to essentially take the derivative of f with respect to y. It's a little confusing though, and I for one wouldn't want to take the derivative of this thing with respect to y. So pictures tend to be a lot nicer. It's usually a lot easier just to graph something. And for semi-stable, you can actually get why the derivative is 0. So yeah, I'd recommend using the picture. But in your book, they might have you do some stuff here. But if we look right here, I take partial f, partial y, that's going to be negative slope, because this value is going down. If it's negative, that's going to be a stable equilibrium point. In this one, we have partial f, partial y is greater than 0. That signifies it's an unstable equilibrium point. And then in the middle here, we actually have partial f partial y equals 0. That one's actually inconclusive. No, let me fix my s. So it doesn't tell you enough information to be able to determine if that's stable, unstable, or semi-stable. Alright, so that was kind of a very brief summary of what this is. And now we're going to do some examples, and hopefully it becomes a little more clear.